All right, let's look at the reactions of esters. So the ester is going to be similar to a carboxylic acid in its reactivity. It's a little bit more reactive than a carboxylic acid, but we can kind of group those together as being similar in reaction conditions. They're going to be less reactive than acid halides and anhydrides, but much more active than amides and nitriles. And in general, the ester will require a strong nucleophile if we're going to have a direct addition. So a good nucleophile, an anionic nucleophile, or at least one of our nucleophiles that we consider to be strong, to react directly with the carbonyl due to reduced reactivity versus the acid halide, for example, resulting in an alkoxide byproduct and a substitution of that OR group. Now, if we do have a weak nucleophile, we can get that to add if we add a catalyst, an acid catalyst, to solution to facilitate the activation of the carbonyl, allowing the nucleophile to replace that OR group with a byproduct of an alcohol. So those are the general reactions that we'll see most of, but there are other variations that we'll look at as well, including reductions in the Baeyer Villager reaction. All right, so what gives esters their reactivity? Where do they rank? Well, they rank here with carboxylic acids, about the same, less reactive than our acid halides and anhydrides because of the leaving group identity. So the first three functional groups have leaving groups after direct addition that are weak bases. And so we have the conjugate bases of strong acids and the bromide and chloride here. Those are the strongest, are the most reactive toward carbonyl addition. Acetate is a weak base, but it's still a good enough leaving group to facilitate direct addition as well. But then when we get to esters and carboxylic acids, we would have these alkoxide leaving groups if we were to do a direct elimination. Now, of course, we will see that in base, the carboxylic acids will actually deprotonate to carboxylates and become even less reactive. But in general, the electron distribution is about the same as the ester. And then the amide has a very difficult elimination to invoke there, the NH2 minus. And then nitriles and carboxylates cannot undergo direct elimination. They have to be activated in acid or by an extremely powerful Lewis acid like lithium aluminum hydride in the case of the carboxylate. Okay, so if we have our esters, where do they sit? Well, here are the reactions that form esters first before we get into the reactions of esters. And the first here is the Fischer esterification. So the mechanism for this is given in the video on carboxylic acid reactions, but it's a carboxylic acid reacts with an alcohol with sulfuric acid and heat to generate our ester, and we get a byproduct of water here. So it's important that this is catalytic sulfuric acid and not necessarily aqueous sulfuric acid. We want to have drops of the concentrated stuff as opposed to a solution because we want to use Le Chatelier's principle to either remove an ester from solution or limit the amount of water that we have present in the final mixture. Okay, so we're going to try to have as little water as possible to make sure we form as much ester as possible. With carboxylates, we can react with primary or secondary halides in order to form esters from an SN2 reaction. So we just see that nucleophilic carboxylate attack. So that's the opposite of an electrophilic reaction. It's actually a nucleophilic addition there in an SN2 reaction to the alkyl halide, and we form our ester in that fashion. Okay. Another way we can form an ester is alcoholysis of our very active functional groups. So we can either take a weak nucleophile and add it directly. If we do that, we are going to get a byproduct of our conjugate acid, either HCl, or if we use the acid anhydride, we'll get a equivalent of carboxylic acid as a byproduct at the end there. Okay. If we do a direct addition, say with an alkoxide, then we'll end up getting a direct addition to form the ester, and then we'll kick off the halide by itself, and then the carboxylate as well. Okay, so if we use the anhydride, we would end up, or kicking off the carboxylate. Now, if we do alcoholysis of an amide, we can only use acidic conditions because there's no great leaving group in the tetrahedral intermediate if we try basic conditions. The best leaving group would actually be the nucleophile. We'll look at this reaction mechanism in the video on amides, but we take a full equivalent of HCl because we're going to end up protonating the amine in the end, taking up our acid, and so we'd like to have excess acid there if possible, at least one equivalent to make sure that this goes efficiently. Okay, not entirely necessary, but it will definitely help out the reaction quite a bit. And then we heat and drive this through an unfavorable elimination of the amine in one of the steps. And excuse me, this will end up being NH4 plus here, not NH3 plus, so ammonium is the byproduct. And again, we'll look at this mechanism in the video on amides. So again, making an ester. The Baeyer Villager oxidation is kind of a more abstract way to make the ester, where we get the insertion of an oxygen from this trifluoro peroxyacetate here. And so this oxygen, one of these three oxygens, the peroxide bond, again there's a separate video on this reaction, will actually insert itself, and then the one of these two R groups will migrate. And so the odds of a migration are greater if that group is a proton versus a tertiary position, secondary, or phenyl position than a primary. And finally, the least likely to move is a methyl. Okay, so again, without getting too much into the Baeyer Villager, if we have this ketone, methyl versus tertiary, if we perform the reaction, we end up with a migration of that methyl group and then insertion of the oxygen in that position versus the insertion on this side. Okay, so that's again a separate video and another way to make an ester. All right, so finally here, the reactions of esters. We will start with hydrolysis. We have for us here hydrolysis in acid first, form a carboxylic acid and an alcohol. So if we treat it with sulfuric acid and H3O+, we want there to be formation of the carboxylic acid, so water is good here, so any aqueous acid will do. But because esters are less reactive than acid halides, we will have to activate our carbonyl first. So we protonate in the first step of the mechanism. At this point, water is our nucleophile because we're hydrolyzing. That's the definition, cleavage by water. And then we've got an active carbonyl, a weak nucleophile, but since we activated the carbonyl, we can attack making our first tetrahedral intermediate. Currently, though, the water that we just added is the best leaving group, and so we want to remove that proton using the solvent. You could also say capital B for base from solution, no problem there on my end, but when we remove that proton, now we have no good leaving group. So any one of these three oxygens would have to take a negative charge to leave. So we know what we're going toward. We're getting rid of the OR group. We're cleaving the ester, and so we'll protonate that OR group here. Now we've got a protonated alcohol leaving group. That's a good leaving group. Very low pKa of that acid. And so at this point, the carbonyl can reform and kick off the leaving group. That will give us our protonated carboxylic acid. That will then be deprotonated by solvent water here to give our carboxylic acid product. A quick note that this mechanism applies to primary and secondary alcohols. Okay, if we had a tertiary alcohol on our ester, so an OR group with a tertiary group, it proceeds by an SN1 mechanism instead. So let's look at how that would occur here. If we protonate first, again activating our system, our carbonyl for addition, we would end up with this carbonyl protonated. And at this point, we would have a rate limiting step where tertiary carbocation formation is favored. And so we would end up with our byproduct here, or excuse me, our carboxylic acid would form, and if I keep my oxygens lined up, the OH would be up top, carbonyl here. So there's our carboxylic acid. And then our carbocation, sp2 planar, trigonal planar there forms here. At that point, we have a water molecule that adds here, and we're still reversible at this point, and we form a protonated alcohol, which would then be deprotonated by solvent, base from solution, to form a tertiary alcohol. Ultimately, though, that carboxylic acid hydrolysis product was formed in the previous 2 steps previous in the mechanism. So it does proceed by a slightly different route if it is a stable cation forming ion on the ester oxygen side there. In basic conditions, this is also called saponification. We're going to need some heat to help out saponification because of a key step here where we have to eliminate a poor leaving group. And so we'll see that in just a moment. Then an aqueous acidic workup at the end protonates the carboxylate to a carboxylic acid. So let's look and see how this works. But saponification, we're going to have good nucleophiles, so we can have a direct addition to form the tetrahedral intermediate to start with. We don't need to protonate first because of that good nucleophile. Well, at this point, our leaving groups are equivalent. Okay, so if we kick off OR minus or OH minus, they are about the same base strength because they're conjugate acids, have about the same pKa. So backwards is possible, but also kicking off in the forward direction is possible. So let's work forward by kicking off the ester group, the OR group, and now we've got a carboxylic acid. Now we would be done if we weren't in basic solution here, but we are. So base will then turn around and react with the carboxylate. And so irreversibly here, strong base, weak acid. It's reversible to a microscopic amount, very tiny amount, but for the most part you're going to see this form the carboxylate in water as a byproduct. And so to go forward here, we would want to add a little bit of proton here. And we could even say that this isn't hydroxide. We could say that it's the alkoxide, but either way, we end up forming net an equivalent of protonated species there. Okay, but either one is fine on my end. Now, the next step, step 2 of the synthesis here, the line reaction, is to then add hydronium. Can't have base and hydronium in the solution at the same time, at least not to invoke for the mechanism here, and so it's not reasonable to invoke for the mechanism in those conditions. So after a time, we then add hydronium, and that gives us our protonated carboxylic acid at the end. All right, so typically transesterification is undesirable. Okay, so this reaction is typically undesirable. There we go. Because it's mixing up two esters that are about the same reactivity. So you can imagine our methyl ester here forming an equilibrium with our new ester and not really either one winning out in the end. That's why they tend to be a little bit annoying to undergo transesterification. And it happens when you mix a solvent alcohol that doesn't match the alcohol that is on the ester. Okay, so that group that gets kicked off in the end, when that doesn't match, that's when transesterification occurs. So let's see it happen in acidic conditions. Mechanism will be very similar to hydrolysis. We have a poor nucleophile, so we must activate first. And again, this time I will use generic base, a conjugate acid here, donating a proton like we saw in class. Now, protonated, we have a good electrophile, so even a weak nucleophile like an alcohol, neutral alcohol, can add to this. So we form a tetrahedral intermediate. Our methyl ester is now a methoxy group, and we have a protonated alcohol that we just added that's currently our best leaving group. So we want to deactivate this leaving group for the forward direction. They're both happening. It's going forward and backward, kicking on, adding back on. But the only way forward is to deactivate that leaving group and then take our methyl ester. I'll draw the methyl out there. And let's actually activate that as a leaving group by protonating. From there, we clearly have a protonated alcohol as our best leaving group. And so we can reform the carbonyl, kick off that leaving group. And now we've got a protonated version of our new ester. That solvent from solution can remove that proton. And there is our new ester in some equilibrium with our original ester. In basic conditions, this can also happen. All right, so if you have basic conditions, we can do a direct addition. So here we are again looking at our methyl group here, our alkoxide. We are not matching it up with our solvent and with our nucleophile. So this is the undesirable scenario, but we can directly add a strong nucleophile to the carbonyl, just like we did with hydrolysis, create our tetrahedral intermediate. Now we've got two equivalent leaving groups. The only way forward, both are happening, but the only way forward is to kick off the methyl group that we had originally. It could be any group. We just defined it as a methyl here to make it different than our arbitrary group that we're adding on. And when that kicks off, we form our new ester and methoxide in some concentration again. Okay, so the basic mechanism is a little bit shorter than is the acidic mechanism. All right, so ammonolysis of esters means we are going to cut the ester with an amine, and that's going to form an amide. We can do this with a catalytic amount of proton because the amide is so much more stable than the ester, the amide bond. Remember, amides are more stable because of the increased resonance effect there with the nitrogen, so we end up with a more stable compound in the end. And eventually it will all convert to amide as long as we only use a catalytic amount of H+. So we don't want to overload the lone pairs of the amine, but we can catalyze this, speed it up with acid here. So what we do, we have a situation where there is catalytic H+, and so since we have that, let's go ahead and protonate our system. What is this H plus probably attached to? It's probably attached to another amine. So this is like an NH3R plus situation here. But we can just identify it as base from solution. Either way, it'll be activated by the increased amount of acidic proton in solution. Okay, so now that we're there, we can attack directly. After activation, we can attack more rapidly and form a tetrahedral intermediate. Well, at this point, the best leaving group is our amine here. And so we want to deprotonate this to deactivate it as a leaving group. Won't happen to a great degree, but it'll happen enough. And now we've got our amine here on our tetrahedral intermediate. And from there, we can activate our ester leaving group. And kick off that leaving group. Base from solution, then takes that proton. So a slight excess of amine wouldn't hurt. Just don't need to have an excess of proton. Okay, but that mechanism is feasible for alcoholysis of esters. Now, esters can also be cleaved by direct addition or basic conditions for amines, because amines are good nucleophiles. In this scenario, we're going to heat a little bit to push this first step along. And if we do this, take our direct addition, we can now remove this proton from the amine and at this point the best leaving group is the OR group. So heating this up more pushes this step along. And the alkoxide can then react with a base from solution that has that extra proton to irreversibly form your alcohol, thereby locking in your amide. Okay, so again, ammonolysis in basic conditions. All right, let's look at some reductions from esters. Lithium aluminum hydride is required, not sodium borohydride, because it's not reactive enough to react with esters. It can react with acid halides, aldehydes, ketones, and anhydrides, but it can't react with esters. Okay, so we won't use that. Lithium aluminum hydride can be represented AlH4, lithium aluminum hydride there. LAH is also an abbreviation. So what do? We take our hydride from aluminum hydride. It acts as a nucleophile to that carbonyl, makes a tetrahedral intermediate. Not reversible because hydrogen is a poor leaving group. At this point, the carbonyl reforms, kicks off our alkoxide, and briefly we get an aldehyde. Okay, but aldehydes react faster than esters do. And so what we'll see is before all the ester can react, we're going to add an equivalent here to the aldehyde, forming another tetrahedral intermediate with no good leaving group. So we get stuck at this tertiary or at this primary carbon. And then step 2 is adding hydronium, step 2 of the line reaction. And we get our primary alcohol. Okay, suppose that you don't want to react all the way to the primary alcohol and you want to stop at an aldehyde when reducing your ester. You can use a reagent known as DIBALH or diisobutyl aluminum hydride. So here's the aluminum hydride part and then 2 isobutyl groups attached. Okay, and at -78 degrees, what will happen is similar to the first step of hydroboration. You're going to have a square tetrahedral, or excuse me, a square intermediate where the forming hydride ion from aluminum will attack carbon, kick up the carbonyl as normal, except it will bond to the aluminum Lewis acid that's freeing up that orbital. Okay, and so what you get out of it is a stable tetrahedral complex where that Lewis acid group is stably hanging on to the oxygen. So what happens is you don't eliminate the OR group immediately. As you warm, you in step 2 warm to room temperature, as you've already quenched the solution with H2O. So all the hydride reagent reacts away, and in the absence of additional hydride reagent, as you warm up, the aluminum is displaced here from your oxygen. So that bond goes back. Presumably water will take the place of that aluminum oxygen bond there. Now that you're free, you can proceed with the tetrahedral intermediate, eliminating the alkoxide. Because you've already added water, you've quenched your remaining hydride reagent, and so you're able to stop at the aldehyde. Mechanism is very similar to what you see in typical lithium aluminum hydride reduction, except for this little trick with the temperature and the tetrahedral intermediate. Negative charge buildup doesn't occur until after you warm the solution. All right, looking here at our esters and organometallic additions, any of our 3 nucleophilic organometallics that we've learned, organolithium, Grignard reagents, and acetylides, can all add to an ester to add 2 different groups. And so you will add whatever metal you're using, you're going to add 2 groups because, again, you kick off that leaving group OR minus in step 1 of the line reaction. So we can use either a Grignard, an acetylide here, or an organolithium to accomplish this. If we show the organolithium mechanism, it's a very polar bond. It resembles a carbanion. You could show it as an R-, that's fine. but you'll make a tetrahedral intermediate irreversibly because we have a new carbon-carbon bond. We will kick off that leaving group, form a ketone intermediate, but then a second equivalent will come in and react pretty rapidly, more rapidly than the ester even. So we can't stop here, and create a tertiary alkoxide, which is stuck until we add acid. Once we add some hydronium to solution, that proton will cap off the tertiary alcohol product. Okay, that would happen for any of these three organometallics. All right, so looking ahead, the malonic ester synthesis, we'll take a malonic ester from malonate or propane dioic acid, ester, so the malonic ester malonate. We take a base that matches our ester to prevent transesterification, and that base will create a carbanon here. That carbanon will attack in an SN2 reaction, either a secondary or primary carbon with a leaving group, and then we hydrolyze the ester and decarboxylate in the final step to form a carboxylic acid. So malonic esters are covered in another video, as this takes a little bit of detail for the mechanism, so please refer to that if your exam requires the malonic ester. Check your list, though it's a later reaction. And then finally, the acetoacetic ester synthesis, same thing. Check your reaction list. Probably won't get to it on an earlier test in the semester, but later for sure. The acetoacetic ester basically takes a beta ketone here, so this is a alpha beta ketone from that ester, beta ketoester, and we're going to deprotonate again at this alpha carbon here with a base that matches the ester group to prevent transesterification. SN2 right on to that group, get an R group there, and then hydrolyze the ester and decarboxylate, and we get a ketone as our product. Again, this is in a different video as well for full account of the acetoacetic ester synthesis.